We know a lot about vectors, but let's see if we can form a matrix by taking a column vector times a row vector and seeing what happens. So let's see, we would take C1 and then C2 here, that would be your column vector, and then you could take the R1 and R2, this would just be two entries in that row vector, and then you can multiply those together. So you put your R1 on the left side here, you get C1, and then you could do that again, so R1 and C2 here. So that would be the left side of the matrix, and then on the right side you would have R2s here, because you put your R2 and then C1 and a C2. And so now we've formed 1, 2, 3, 4. It's a 2 by 2 matrix. Matrices have special rules for addition and multiplication, so if you want to add them, you need to have the same dimensions. You could take an IJ matrix, and you can add that to another IJ matrix, and that would just give you another IJ matrix. For the multiplication, we also have to keep track of the dimensions, but in a different way. So let's say we take our IJ matrix. Now we'd have to find a JK matrix to be able to multiply those together. And then we can cross these out, kind of like that. And then we'd be able to get something that's IK matrix. The cool thing about the addition is that you can change the order. So let's see if we could set up an example. We have something like B plus C, and we're just multiplying that by the A. So you could get something like AC plus AB in the end, because you can basically just swap the order of the addition there. However, for the multiplication, you can't change the order. So you'd have something like A times parentheses BC, and you can move the parentheses around, but you can't change the orders of the letters. So it would have to be like AB in the parentheses there times the C. So let's make a note that you can't change the order for the multiplication, and so in fact AB does not equal BA, most of the time at least. Multiplying matrices is just like taking a bunch of dot products. So let's say we have matrix A times matrix B, and that's going to be equal to matrix C. So we would take the first row from matrix A over here, and then we're going to take the dot product with the matrix B's first column here. So you take this entry times this entry plus this entry times this entry. So you take a little dot product there. So the sum of that dot product is going to go right here as being the first entry in the matrix C. And then we're going to take the next row from A and do another dot product with the first column of the B here. And then that's going to be our next entry down here for C. We can write this a little more mathematically by saying that A times the B1 and the B2 columns, these are the columns, this is just the whole matrix, is going to be equal to A times the column 1, which is what we did over here, and then you get another column over here, which is going to be A times column 2. Let's take a look at a partition matrix. So that's just basically going to be 1, 2, 3, 4 matrices inside of 1. This is going to be 1, 2 matrices inside of 1. This is a 2 by 3 matrix, and this is a 2 by 2. This is a 1 by 3. This is a 1 by 1. Well, let's see if we can analyze that a little better. So we have 2 rows here, and of course that's going to carry across here to 2 on that one. And here, this one also has 1 row, and that's going to carry across over here. You're going to have 1 there. This one right here is going to have 3 columns, so we have 1, 2, 3 columns, and that's going to carry down here into this one. And this one has 2 columns, 1, 2, which is going to carry down here. And let's do the same thing over here. So we would see that this particular row has 3 rows, 1, 2, 3, and this one has 2, 1, 2. So we actually have 5 rows here. And then over here we have 2 columns, 1, 2. And we notice how these 5 rows have to match those 5 columns. So far so good. Now for matrix C, we're going to notice that the top side simply has 2 rows, and then there's a 1 row there on the bottom that's just going to carry across. And in the top, there's actually just going to be 2 columns in total here, because this is a sum. And so everything here has actually only 2 columns. Well, let's see how we were able to find this final matrix here. So we have to take the dot product. So we're going to take this row and multiply it by this column. So we take this thing times that thing, this thing times that thing. if we do that, let's say 2 by 3 multiplied by a 3 by 2, we're going to notice that the 3's will cancel out, and you're going to be left with a 2 by 2. And that's this piece right here. And then you kind of do the same thing for this times that, and well, your 2's will cancel, but you're just going to be left with another 2 by 2, which is what you have over here. When you add those together, you're just going to get a 2 by 2. Remember, your additions have to be the same. And then you can do the same thing over here, multiply this by that, take the sum. And if you take 1 by 3 multiplied by a 3 by 2, again, the 3's are going to cancel. You're going to be left with a 1 by 2. And over here, if you multiply the 1 by 2 by a 2 by 2, the 2's will cancel, but you'll still be left with a 1 by 2, which is what we have here. When you add those together, then you get your final C matrix here. That process is simply known as block multiplication. So we would take, this is matrix 1, 2, 3, and 4, where these are not going to be the dimensions, but rather just placeholders. And over here we have matrix 1 and matrix 2. And then when you multiply them together, you get the dot product. So you take this times that plus this times that. B1 times the A11 plus the B2 times the A12. And then on the next row, you get something like B1 times the A21 plus the B2 times the A22. Well, enough about that. Let's see if we could take the transpose of a matrix, which is going to be the A to the T. And that would be being able to go like Aij, and then translating that into an Aji matrix. So we've got a matrix that's A, 1, 2, 3, 4, 5, 6, and we could take the A to the T, the transpose, and that's simply just going to be like, let's flip that and make it 1, 2, 3, and then let's flip that over here and make that 4, 5, 6, and so now we've taken the transpose. Well, you could probably guess if you did this again, then you would get something like this. A transposed sends you straight back to the A. Another law of the transpose is going to be if you have an A times a B and you transpose that, that's simply going to be B transposed times the A transposed, and that order has to be very specific. And that's because this is multiplication. But when you have the addition, you could say A plus B, and this is transposed here. That's going to be something like A transpose plus B transposed. And so you could flip these however way you want. Let's just be careful that if we have an A transposed times an A, that is not going to be the same as A times A transposed. So far we've discussed these rules that can apply to any dimension of matrices. But let's talk about square matrices, which are very special. And one of the key square matrices are going to be identity matrices. So it's saying something like I times A is simply equal to A, which is equal to A times I. This kind of contradicts this rule over here. But the cool thing is that these I's will basically cancel out, because it's kind of like saying 1. 1 times A is equal to A. But it gets better for the identity matrix, because if you take the inverse of the identity matrix, it's also going to be equal to the same matrix. And you can also take the transpose, and it's going to be equal to the same matrix. So they're kind of just very special matrices, just like the number 1. A very special thing we do with these identity matrices is we can augment matrix A by an identity matrix. And if we do that, it's just going to look something like this. It'd be like A augmented by a 1, 0, 0, 1. You take the same dimension. After that, you're going to do some row operations, and you're going to find that you're going to get an I augmented by the inverse of A over here. And so that would look something like 1, 0, 0, 1 augmented by A minus 1, A minus 1, A minus 1, A minus 1. These are just the entries of the inverse of the matrix. But before we talk about the invertible matrices, let's talk about exponents. So we'll have something like A to the third is going to be A times A times A. We could also say A to the 0 power, that's going to be equal to I. Same dimensions there. A to the power of negative 3 means that you're going to say A and then negative 1, A, negative 1, A, negative 1. Here it's kind of like all to the power of 1, so you're going to add them all up. 1 plus 1 plus 1. Here, minus 1, minus 1, minus 1. You could also have A to the power of a third, which implies that there are going to be 3 B's which multiply together to equal an A. Let's take a quick peek at the invertible matrix, and all that means is that you could take a matrix A, and let's say you wanted to get to an I. All you need to do is multiply that by the inverse, and it doesn't matter which way you do this, so you could do it from the left side, or you could do it from the right side, and then you'll still get an I there. That's pretty nice. And as you might expect, you can also take a matrix that has been inverted and invert it, and then just get your original matrix back. And you could play a little game with the transpose and the inverses as well. So you could say the A inverted transposed is going to be equal to the A transpose inverted. Now, one reason to find the inverse of a matrix, let's say you had your matrix equation AX equals B. You can actually easily find the solution to this equation, the X vector, by multiplying the left side here by the inverse of A, and that'll literally just go away, and you have to do the same thing on the right side, of course. So that would just be equal to the A inverse times the B. And notice how we had to do this from the left side, so it appeared on the left side over here as well. But that's your solution there. You're already done. If you happen to know the inverse, you're done. Boom! One last quick note is if we know that both A and B are invertible, then we could take A times B and take the inverse, and that's simply going to be equal to B inverted times A inverted, and that's going to be the same rule that we had for the transpose over here. In other words, what this is saying is that if we have an A, B equals C idea, then we could take C to the negative 1, which is going to be equal to B minus 1 times A minus 1. Let's now turn our attention to the elementary matrix, which is pretty important. Let's say we wanted to find, transform our A into an I. We could do that by taking a series of row operations, right? Like we would usually do. Or you could multiply it by some matrix. And hey, if it was the inverse, then boom, right there, you'd have the answer to that. Or you could take multiple steps to do it. It doesn't have to be in a single step. So you could say E1, E2, maybe even an E3 over here, and then all that would be equal to I. Let's say you wanted to reverse this process and get back to A. In order to do that, you have to multiply both sides by, on the left side, by the inverse of E negative 1. So that way this goes away, and over here you get something like I times the inverse of that 3E. And then you kind of keep doing this, so then you'd have to do it again for the E2. So on the left side you get E2 inverted. And then boom, you do it again for the E1, and now you've gotten rid of everything on the left side, but now you get this on the right. But what we could also do is simply multiply both sides on the right side by the inverse of A, getting rid of the A on this side. And so you get something like E3, E2, E1, and then we got rid of our A. But how do we do that? Well, we had to multiply both sides on the right side by the inverse of A. And now here's the quick neat trick about this is remember the I's fall off, and that you get that A is equal to all this, and the inverse of A is equal to all that. What? Now let's attempt an LU decomposition. We see here that this is going to be a regular old matrix equation. So we've got a matrix times the X equals some B. What I'm going to claim is that we could take our A and we could break it apart and form an L and a U matrix out of it. So we're going to take our 1, 2, 3, 4, and somehow that's going to be equal to a lower triangular here, which means it's going to have a 1, and there's going to be a 0 there, and then there's going to be something over here. This could obviously extend to become 3 by 3s or 4 by 4s or whatever. But over here, we have a U1, a U2, and down here is a U3, whereas over here we have the 0. Because now we can see how this is going to be the lower triangular, and this is going to be the upper triangular, and this is the format for those. And recall from before that this is simply a matrix multiplication, so we're going to find the dot product of that. So we're going to go 1 times U1 plus the 0 times 0. And we're just going to get in the first section U1. And then we're going to do the same thing with this one. So L times U1 and 1 times 0, that's just going to add up to be LU1 right here. So we're done there. And then we could do the same thing for this one. So 1 times the U2, 0 times that, that's just going to give us a U2 over here. And if we take the next row, then we could take L times U2 there. L times the U2 plus 1 times the U3. And so now we figured out what the dot product is. Now this can actually be the standard formula for a 2x2 decomposition, and you would have a standard formula for every decomposition, or 3x3 or 4x4, but I'm just going to write out the 2x2 because that one's relatively simple. Well, from here it's not hard to see that U1 equals 1, and U2 equals 2. And if L times U1 is equal to 3, and U1 equals 1, then L, it must equal 3. And finally, we could see that if L times U2, that's going to be equal to 6, plus U3 is supposed to be 4, then that means that U3 is equal to -2. Now if we were to check our work and plug these values that we found back into the original LU matrices and see if this works, let's see if we do that. Well, we already know that the L's, this one's the easy one because it's just 1, 1, 0, and we just need one value here, which is the 3. So now we form the L, and then we have the U, which is going to be, well, it only has 1, 0 here, so we're going to need all three of these. So we have the 1, we have the 2, and then we have a -2 over here. And if we try to multiply those together and get the dot product, well, let's see. So you're going to get a 1 plus 0 for this one, it's just 1. And then you're going to get like a 3 plus a 0 is going to give you a 3 right here. And over here you're going to get a 2 plus the 0 gives you a 2. And here you would get a 6 minus 2, which gives you 4. And so we were right. From here we have to set up two very special equations. L times some y vector is equal to b, and u times the x vector is equal to that y vector. So let's set this up. We know that the L matrix is going to look something like a 1 and a 3. And then there's going to be like a 0 and a 1 over here. And then we're going to multiply that by this y vector. So it's going to be like a y1 plus a y2. And that's going to be equal to this b, which is just 5, 6. That. And that's the first equation. In order to set up this next equation, we need to first find this y vector. So let's set up our y1 and our y2, and let's see if we can figure out what that equals. Well, it turns out that y1 plus 0 y2 is going to equal 5, so obviously y1 equals 5. And 3y1 plus 1 y2 equals 6, so if we do the math on that, we're going to find that it's equal to -9 over here. And so we figured out what our y vector is. So let's set up the next equation. We're going to start with this U matrix, which we know is supposed to be 1, 0. And then we can go ahead and add that to this next one, 2, -2. Keeping in mind that we're going to need to multiply in between here these x1s plus the x2. And that is going to be equal to the y vector we found before. So now we have 5, -9. And we can try to solve for our x's. Well, just like before, we're basically going to have to solve some equations here. So we can see that 0 times x1 and then minus 2x2 is going to be equal to this -9. So from here we can conclude that this x2 is going to be 4.5. And from there we can say that x1 plus 9 is equal to 5. So it gives us that -4 is going to be equal to this x1. So there you have it. We found our solution to this equation using an LU decomposition, although it was pretty complicated. However, it seems like as the matrices get bigger, then finding the LU decomposition becomes a little simpler. Let's see if we can take our A and do a couple of steps to transform it into echelon form, which is basically what the upper triangular is. So this would become something like a 2, 2, 1, and the next row would be a 0, and then here you'd get a 3, and here you'd get a 4, and then over here it'd be a 0, and you get a 3 and a 6 over here. And if you take it one more step, then you get a 2, 2, 1, 0, 3, 4, and then over here it's just going to be a 0, 0, 2. And so we've already found the U, and it turns out the L is just as easy to find. Let's see if we can figure out what we know so far about the L. It's just going to be a diagonal set of 1s here, and then we have a 0, 0, 0, and we only need to find 3 little pieces here. In order to do that, let's take a look at our pivots. Here is the 2, that pivot. All we need to do is transform it into a 1. So we're going to divide this whole thing by 2, and then we're going to get this first column here. So it'd be a 1, a 2, and a 3. 1, 2, and a 3. And that gives us our first L column. We still don't know what this one is, but we're going to be able to do that by looking at this step. Let's see if we can set up what we know so far. It's going to be 1, 0, 0, and then we have a 2, 1, 0, and a 3, and a 1. So in order to find this spot right here, we're going to look at this column. And we're going to find our pivot, which is going to be this spot right here, that 3. And in order to take that 3 and turn it into a 1, we're going to have to divide this whole thing here by 3. And so we're basically just dividing all this by 3. Whereas over here we divided all this by 2. And so now we're left with a 1 down here. Does that make sense? Now we can claim that if we have L times U equals A, that's kind of like A times B equals C. And so we can derive that if we take the inverse of A, that's simply going to be equal to, you got to switch those, so it's going to be U to the negative 1 times L to the negative 1. So let's see how much information we can gather if A is invertible. Well, the definition of an inverse is that the inverse of A is equal to 1 divided by the determinant of A times the adjunct of A, which is some matrix over here. We'll have to figure out what the adjunct is in some other video. But from here, we can realize that the determinant of A cannot be equal to 0, because otherwise this equation wouldn't work right here. Another thing we know is that since A is invertible, it means it's a square. And so the rank of A is going to be equal to n. Essentially, the number of rows is going to be equal to the number of columns. But since rank of A equals n, that means that x is equal to 0 is the only solution to the equation ax equals 0. And there's another way of saying that the null space of A is equal to simply the 0 vector. And we could say that the dimensions of that null of A is going to be equal to 0. We can also say that the columns of A are linear independent. And so we could also say that the columns of A span R to the n. And we could say that the column space of A resides in R to the n. And it's actually equal to R to the n. We also know that the transformation associated with that matrix is both onto and 1 to 1. We also know that A will reduce to an I if we were to do that in echelon or reduced echelon form. And we can even say that CA is going to be equal to I, and also that AD is going to be equal to I. There's definitely going to be some C and some possible D that we can create an I from that. So this is most of the information we can get if A is invertible, but there's some stuff we haven't covered yet, like the adjunct, maybe this determinant, this null space, the dimensions, and some things like that. But we're going to have to do that in another video.